So in this video, what we're going to do is we're going to take a look at what are called the comparison tests. And these are tests to prove whether or not a function actually is, a series is divergent or convergent. And so basically what we're going to do is we're going to do some manipulation that will allow us to, in fact, compare our function to ones that we know are already convergent or already divergent. What I want you to pay attention to as you're doing work here is how it is that I'm actually proving what I'm proving, how I'm selecting the functions that I'm going to be comparing against, right? Because that's actually really crucial to proving that these things are convergent. Remember that we don't want to just show that something, we don't want to just say that something's convergent or divergent. We actually need to show that it is in fact convergent or divergent. And so what we're going to do is we're going to utilize these tests in order to do that. Okay? All right, so let's get started. So we'll begin with a theorem. And so this theorem is our comparison test theorem. And it says, suppose there exists an integer n such that 0 less than or equal to a sub n is less than or equal to b sub n for all n greater than or equal to, and this big N is like a big arbitrary number. We actually are going to figure out what that number is, but it's just, there's got to be a sub number at which our b sub n is going to end up being bigger than a sub n. Okay? If the sum n equals 1 to infinity of b sub n converges, then the sum n equals 1 up to infinity of a sub n converges. So basically, if we know that we have a series, okay, b sub n, which is greater than a sub n, right? So we know that b sub n is going to be greater than a sub n, right? And let's imagine we'll pick an n greater than or equal to, we'll use 3. So what that means is that b sub 3 is greater than a sub 3, b sub 4, or greater than or equal to. B sub 4 is greater than or equal to a sub 4. B sub 5 is greater than or equal to a sub 5, so on and so on and so forth. Okay, so basically we've got this sequence that dominates, right? It dominates a sub n, all right, on the larger side. And so what that does for us is that it tells us that if the dominant sequence, right, okay, if that converges, or the dominant series converges, then we know that the one that's actually less than that is also going to converge, right? And it kind of makes sense because if b sub n ends up going down, giving us a finite number, then a sub n should as well when you summate it, because every single term is going to be less than all the terms of b sub n. That's kind of that idea. And then we have vice versa, which is our second one here, number 2, and that's suppose there exists an integer n such that a sub n is greater than or equal to b sub n, which is greater than or equal to 0 for all n greater than or equal to n. Now, if the sum n equals 1 up to infinity of b sub n diverges, okay, then the sum n equals 1 up to infinity of a sub n diverges. All right, now this is the opposite case. Now we have our b sub n's, right, okay, are less than or equal to our a sub n's. And so again, we can pick an arbitrary, for, say, n greater than or equal to 5. And now we say, okay, well, b sub 5 is less than or equal to a sub 5, and b sub 6 is less than or equal to a sub 6, and so on and so on and so forth. Now, if the b sub n's, right, if the sum n equals 1 up to infinity, that series of b sub n's diverges, the ones for a sub n have to diverge as well. They just have to, because they're all bigger than the b sub n's. So if the b sub n's continue on into infinity, or the sum of them continues on into infinity, then the sum of the a sub n's has to as well, because they're all bigger. Okay? And that kind of just is meant to kind of give us a kind of relationship between what it means to converge and what it means to diverge. So let's ask ourselves, does the sum k equals 1 up to infinity of 1 over k to the 6th plus 3k plus 10 converge or diverge? And in this case, I look at a function like this, a series like this, and I think to myself, you know what, I want to use a comparison test, because what I've got essentially here is I've got 1 over some kind of polynomial or rational function. And so the comparison test might be really useful for this particular circumstance. So what I'm going to do is I'm going to say, well, I kind of look at this, and I'm going to end up getting 1 over a big number, okay? And that's going to go to 0, and it's going to go to 0 pretty quickly, right? Because this is a k to the 6th term that's in the front. But does it go quickly enough, right? And I don't have anything that quite matches this, all right? So what the trick is going to be here is the trick is going to be about selecting the right function and then having the right reasoning for why that function shows us that this particular series is going to converge. So the first thing that I'm going to need to do is I'm actually going to need to first, I'm going to need to pick a function that converges and is greater than or equal to our function, our sequence rather, I should say. All right. So what I'm going to do is I'm going to notice that I'm actually not going to compare to 1 over k to the 6th plus 3k plus 10. What I'm going to do is I'm going to say, okay, well, k to the 6th plus 3k plus 10. If I can find a function that is actually smaller than that value, all right, for every value of k greater than or equal to I don't know, some arbitrary number, n, k, whatever, then what I have is that I have that 1 over that number is actually going to end up being bigger. Okay? So I'm actually going to switch these out. I'm going to make them n's. I'm going to make them n to the 6th plus 3n plus 10. Okay? And what I'm going to do is I'm going to compare this. I know actually this is going to be greater than or equal to n to the 6th for n greater than or equal to 1 as 3n plus 10, okay, is going to then be greater than, it's going to be strictly greater than 0, right? So basically what we're going to do here is this part here is a positive number, all right, and then the rest is just exactly the same. So we're going to take the same number and add a positive number to it. So consequently, we're going to get that the one on the left-hand side, n to the 6th plus 3n plus 10, is going to be greater than or equal to n to the 6th. Okay? And since that's true, if we take its reciprocal, then 1 over n to the 6th plus 3n plus 10 is going to be then less than or equal to 1 over n to the 6th for n greater than or equal to 1. Okay? That's the flip side. So if you know that the thing on the bottom is bigger than the thing on the bottom for the other one, then when you take the reciprocals, you end up with the exact opposite relationship. Okay? So what this shows me is, okay, that 0 is less than or equal to a sub n, which is less than or equal to b sub n, if, and we say a sub n equals 1 over n to the 6th plus 3n plus 10, okay, and b sub n is equal to 1 over n to the 6th. So that's good. That's good to go. That's actually the first part of our proof. That's the first thing that we need. The second part that we're going to need is we need to show 1 over n to the 6th is convergent. So in order to do this, we're actually going to utilize p-series. The idea is a p-series. So what we know is we know that the sum, n equals 1 up to infinity, of 1 over n to the 6th, right, is a p-series. With n equal to 6 greater than 1. And so, the sum, n equals 1 up to infinity of 1 over n to the 6th, is convergent. That's our requirement as a p-series. All right, so great. So that's the second part. We've actually shown convergence there. So the third part is just to state, thus, by the comparison test, our function, the sum, or rather our series, the sum, k equals 1 up to infinity of 1 over k to the 6th plus 3k plus 10 is convergent. And that finishes it. So we've got 3 parts here. One is we need to find a function, b sub n, that's going to be either greater than or equal to or less than or equal to a sub n, okay, for every a sub n. So the first part is to find this function, right? The second part is to determine whether or not the function that we've shown is either convergent or divergent. We have to actually show it. You might already know, but you do have to show it. It's actually really important. And then finally, you have to state by which test that you used how it is that you know that your series is in fact convergent. And so in this case, thus by the comparison test, we know the sum, k equals 1 up to infinity, of 1 over k to the 6th plus 3k plus 10 is convergent. So let's take a look at another example. Let's say, for example, that we want to know, does k equals 1 up to infinity, a 3k cubed over k to the fourth plus 7k plus 2 converge or diverge? And in a very similar way, we're going to actually go out and we're going to try and figure out if we're going to get convergence or divergence here as well. Okay? Now, the thing that we're going to notice here, though, is that I've got 3k cubed on the top. Right? I got 3k cubed on the top. And so, consequently, I mean, we're looking at something a little bit different. Right? It's not a simple reciprocal in this case. It's actually something that where we're going to have to do a little bit of an algebraic manipulation. But I still want to use the comparison test here. I still want to use the comparison test because it's going to end up becoming, it'll end up becoming very clear as to what our comparison actually should be. Now, I'm going to just use a little thumbnail sketch, and this is not exactly how things go, but this at least gives me my intuition as to why I should actually kind of think that maybe this particular sequence is going to diverge rather than converge. Okay? And so what I want to notice is that what I've got here is I've got k cubed on the top, okay? And then on the bottom, I've got some kind of like k to the fourth, all right? Okay, I got like k to the fourth. And so like, if I kind of think that through, that's going to end up becoming, right? This is going to end up being like k to the negative 1, all right? And so I'm kind of thinking to myself that in some ways, this is going to be that what's going to end up happening is I'm going to end up having this not really actually shrink fast enough, okay? Because when I kind of simplify down my bottom term, that highest power, the dominant power k to the fourth, right, is not quite big enough, okay, for me to have a convergence series, all right? And so what we're going to do is we're actually going to show that that's in fact the case. But the problem is that it's not as simple as, if you remember in the last example, we said, okay, well, we've got k to the fourth plus 7k plus 2, okay, is going to be greater than or equal to, right, k to the fourth, right? And so we'd have 1 over k to the fourth plus 7k plus 2 will end up being less than or equal to 1 over k to the fourth. Well, that's the wrong relationship, right? This is the relationship for convergence. That's not the relationship for divergence. And so what we need to do is we actually need to get something that's actually the other way around, right? We actually need to get something that's actually, in fact, the other way around. So what I'm going to do is I'm going to be kind of clever here, okay? I'm going to actually say, well, if, right, k is greater than or equal to 2, then what we'll notice is that 7k, right, which will equal 14, is going to be less than or equal to, is actually going to be strictly less than, less than k to the fourth, or 2 to the fourth, which equals 16. All right, so 16 is bigger than 14. And so what that's going to allow us to do is, so k to the fourth, okay, is going to be greater than or equal to 7k. And so we'll actually do a substitution there. We're actually going to switch that out, okay? It's going to be greater than or equal to 7k. And, all right, if k is greater than or equal to 2, then 2, right, is going to be less than k to the fourth as well. So that's actually going to be our second piece right there, okay? Now, what that's going to do then is it's going to allow us to substitute. So that's going to be then that k to the fourth plus 7k plus 2 is going to be now less than or equal to, strictly less than or equal to, k to the fourth plus another k to the fourth, right? The second k to the fourth that goes along with the 7k, okay? Plus another k to the fourth that goes with the 2k, so that equals 3k to the fourth. And so now that actually has the right relationship that we need. So what that means is that 3k to the third over k to the fourth plus 7k plus 2 is now going to be greater than or equal to 3k to the third over 3k to the fourth, which is equal to 1 over k. With that stated, what that means is that now we actually show this thing here, 1 over k, is in fact divergent, right? So our function is, or our series is going to end up being bigger than the chosen series that in fact diverges, and so by the comparison test, that's going to actually allow us to state that this is a divergent series. Okay, so that's the first part. So now we're ready to prove. So 1, okay, we'll let a sub k, or we'll use a sub n in this case, equal 3n, excuse me, we're going to let b sub n equal 3n cubed over 3n to the 4th, which equals 1 over n. Then we're going to take a sub n, and that's going to equal now our given sequence, 3n cubed over n to the 4th plus 7n plus 2. Okay, so what we proved just above is a sub n 0 less than or equal to, b sub n less than or equal to a sub n for n greater than or equal to, and it's important that that's only going to be true for greater than or equal to 2. Okay, when n is greater than or equal to 2. So now 2, we're going to say the sum, n equals 1 up to infinity of 1 over n, is divergent as it is harmonic. That's our harmonic divergent sequence, or you can actually say it's a p-series with p equal to 1. So 3, by the comparison test, right, the sum n equals 1 up to infinity of 3n over n to the 4th plus 7n plus 2 is divergent. Okay? And what we want to notice there is notice that in this case, our b sub n, our chosen function, is less than or equal to a sub n, right, for some given arbitrary value of n, right? And our selected function is actually divergent as well. And that's the only direction that we can use in order to prove this. Okay? All right, so let's ask one more question here. Does this series now, the sum n equals 1 up to infinity of 1 over the natural log of n, converge or diverge? And so if I look at this, I now notice that I don't have like a power of n. But what I do have is I do have something that's fairly easy to compare it to. Okay? What I know is that n is going to be greater than the natural log of n. Right? For n greater than or equal to 1. And you can go out and you can check that out, but that's absolutely true. N is what's called a linear function. Natural log of n is a logarithmic. And so consequently, n is going to grow bigger than the natural log of n. All right? Just absolutely the truth. Right? You can even look at a graph. Right? Here's natural log of n. And here is y equals n. Okay? Or y equals x. Right? And y equals the natural log of x. So that's actually going to be true. So n is strictly greater, or we'll take greater than or equal to, the natural log of n. So what that means is that 1 over n is going to end up being less than or equal to 1 over the natural log of n. Okay? And what we also know is that the sum, n equals 1 up to infinity of 1 over n, diverges. So that actually gives me the second part here. So that's kind of perfect, right? Okay, we're going to take 1. We're going to let b sub n equal 1 over n, and a sub n equal 1 over the natural log of n. Okay, and now I'm actually going to write out, if I were going to just write this out as an answer without the work, I would say as n is greater than or equal to the natural log of n, okay, for n greater than or equal to 1, 1 over n is going to be less than or equal to 1 over the natural log of n for n greater than or equal to 1. Thus, that's going to be giving us thus 0 is less than or equal to b sub n, which is less than or equal to a sub n. That's the first thing that I need. The second part is the sum n equals 1 up to infinity of 1 over n diverges as it is harmonic. Okay, this is harmonic. And then 3, the sum n equals 1 up to infinity of 1 over the natural log of n diverges by the comparison test. And those are the 3 parts to my proof. All right, I have found a function that is in fact less than or equal to the function that I'm trying to make a decision on for all values n greater than or equal to 1. I showed that that function in fact diverges, and so that means that my function diverges as well by the comparison test. So now we're going to take a look at another comparison test, and this one's called the limit comparison test. And we're going to actually, in general, we're going to consider a sub n, right, to be the function that we're testing. And b sub n is going to be a selected function, a special selected function. And what we're going to use is we're going to use these 3 principles to determine basically if a sub n either converges or diverges. So on the one hand, we have number 1, which is that the limit as n goes to infinity of a sub n over b sub n equals some value not equal to 0 and not equal to infinity. Okay, so it actually equals value at limit. And in this case, that's basically telling me that a sub n and b sub n are both growing essentially at the same rate. Okay, they're growing at the same rate. So consequently, if they're growing at the same rate, then both will either diverge or both will converge. Either way, okay? Number 2, if the limit as n goes to infinity of a sub n over b sub n is equal to 0, that now means that b sub n is growing faster than a sub n. So if b sub n converges, that means that a sub n is going to converge. And then number 3, if the limit as n goes to infinity of a sub n over b sub n is equal to infinity, and the sum n equals 1 up to infinity of b sub n diverges, well, b sub n is now growing slower than a sub n, right? Because a sub n is dominant here in this case. It's growing bigger. That's why we're going up to infinity. And so that means that the sum n equals 1 up to infinity of a sub n is going to diverge. And that's what's going to happen there. So what we're going to do is we're going to take a look at three different cases here and see how it is that we utilize this limit comparison test. So let's consider this question. Does the series, the sum k equals 1 up to infinity of 1 over 5k to the 5th plus 8k to the 11th converge or diverge? And so what I'm going to do is I'm going to actually select a b sub n, okay, a value of b sub n that's going to allow me to then take a limit, okay? And like limits are a bit easier to use than these summations, right? Because we have some very clearly defined ways of working with limits, right? So I'm going to actually select, I'm going to let b sub n equal 1 over 8k to the 11th. Basically, I'm going to choose the value of, or the highest power on the bottom, okay, to be my comparison, or my comparison that I'm going to take the limit of. Now what I'm going to do is I'm going to do exactly this. I'm going to take the limit as n goes to infinity. So the limit as n goes to infinity of, in this case, 1 over 5k to the 5th plus 8k to the 11th divided by 8k to the 11th. All right? Or, excuse me, divided by 1 over 8k to the 11th. And what that's going to be is, so we're going to invert and multiply. So this is going to end up being the limit as n goes to infinity of 8k to the 11th over 5k to the 5th plus 8k to the 11th. Well, you don't need to actually go in and do L'Hopital's. You know that this is going to end up equaling 8 over 8, okay, which equals 1. So it's going to end up equaling 1. So we have that first requirement, right? We have that it actually equals 1 for the number 1. Now I need to figure out if 1 over 8k to the 11th actually diverges. So the sum, k equals 1 up to infinity, okay, k equals 1 up to infinity of 1 over 8k to the 11th, is actually equal to 1/8 times the sum k equals 1 up to infinity of 1 over k to the 11th, which is a p-series, with p equal to 11, which is greater than 1. And so the sum k equals 1 up to infinity of 1 over 8k to the 11th converges. So that sum actually converges. All right. Now what does that mean? That means that our a sub n, the series that we were trying to figure out if it converged or not, actually also converges. So by the limit comparison test, the sum k equals 11 up to infinity of 1 over 5k to the 5th plus 8k to the 11th converges. Great. So we've actually got our 3 steps here too. We've got 1. We've selected our b sub n, which is 1 over 8k to the 11th. That's just going to take a little bit of scratch work. Then what we do is we show that that limit actually ends up converging to the value, to some value not equal to 0 and not equal to infinity, 1. And so that means that we've got to figure out what happens to 1 over 8k to the 11th. Well, since that series actually converges, that tells me that the series that I wanted to test also converges. So now let's consider this series, the sum n equals 1 up to infinity of 2n squared plus 3n over the square root of 5 plus n to the 5th. Does it converge or diverge? All right, and so we're going to think to ourselves, okay, the limit comparison test might be really handy here, because what I have is I have two pretty complex polynomials on the top and the bottom. It's actually, they're not, the bottom one's not polynomial. It's a square root function, but they're both rational, so we've got our rational functions. And so what I want to do is I want to say, okay, well, I don't know if the comparison test is going to work out so well here, but I think maybe the limit comparison test will. All right, because the limit comparison test, I can take that limit, and that might actually be really very valuable for me, okay, or really handy. So now I'm going to look at this function. So I've got 2n squared plus 3n divided by the square root of 5 plus n to the 5th. And when I look at this, what I'm going to notice is that the dominant part on top, okay, is the 2n squared. So I'm going to take 2n squared on the top, and then on the bottom, the dominant part is n to the 5 halves. Okay? So basically, I take the dominant part of the top, right? So this one's going to end up being my a sub n. And the dominant part of the top is my n squared, and the dominant part on the bottom is going to be the 5 halves, right? Because this is to the 1/2, right? Okay, or that's the 1/2 power, so it ends up n to the 5 halves. So b sub n is going to equal this, and that's going to then end up equaling 2 over n to the 1/2. So now I've kind of selected my values, so I'm going to begin my work. So the limit as n goes to infinity of 2n squared plus 3n over the square root of 5 plus n to the 5th. And what I'm going to do is I'm going to divide that through by 2n squared or n to the 5 halves, which is going to equal then 2n squared plus 3n, okay, times, and then this will be 1 over 2n squared. So what's going to happen actually, so we've got this is, by the way, it continues to be a limit, 5 plus n to the 5th. What's going to happen is we'll multiply by n to the 5 halves, okay, divided by 2n squared. Now the thing about this is that we don't actually want to do anything with 2n squared. We don't want to multiply it by the square root of 5 plus n to the 5th. We actually want to do something with it up here, okay? So that's really like the equivalent of writing this as the limit as n goes to infinity of 2n squared plus 3n over the square root of 5 plus n to the 5th times, and this will be 1 over 2n squared, and the bottom one will be 1 over n to the 5th, or n to the 5 halves, excuse me, n to the 5 halves. So now this is going to be then equal to the limit as n goes to infinity, and this will be 2n squared over 2n squared plus 3n over 2n squared divided by, and this will now be the square root of 5 over n to the 5 halves plus n to the 5, or excuse me, then plus n to the 5th, sorry, n to the 5 over n to the 5, okay? Right, because that half, the half term is the square root term, we just bring the square roots in, okay? So this is going to then equal the limit as n goes to infinity of 1 plus 3 over 2n divided by the square root of 5 over n to the 5th plus 1. Okay? Now this is going to then equal, well, as the limit as goes to infinity, this goes to 0, and this part goes to 0, so what we're left with is 1 over the square root of 1, which just equals 1. So that's an actual term, right? That's actually a value. That's our limit equals an L. So now we have to determine, right, if 2 over n to the 1/2 is in fact divergent or convergent. So the sum, n equals 1 up to infinity, of 2 over n to the 1/2 is going to equal 2 times the sum, n equals 1 up to infinity, of 1 over n to the 1/2. Okay? As the sum, n equals 1 to infinity of 1 over n to the 1/2 is a p series with p, less than or equal to 1, the series diverges. Hence, by the limit comparison test, the sum, n equals 1 up to infinity of 2n squared plus 3n over the square root of 5 plus n squared, or 5 plus n to the 5th, 5 plus n to the 5th, diverges. All right, so what about this? Let's say, for example, this series, we got the sum n equals 1 up to infinity of n to the 4th minus 6 over n to the 9th plus 3n squared plus 4n plus 1. Does it diverge or converge? Now, the fact of the matter is that we can actually go in and we can utilize a couple of different things in order to figure out if this sequence converges or diverges. Let's take, for example, let's actually utilize, our basic principle that we've been using. And so we'll take the dominant parts of the top and the bottom. So I'm going to let my b sub n equal n to the 4th over n to the 9th. Okay? Which is going to equal 1 over n to the 5th. And what I know is that if I take that series with 1 over n to the 5th, that's a p series that's going to converge. All right? So what I really want is I want to see if I'm going to get a convergent series here. Okay? So I'm going to take the sum, n equals 1 up to infinity, okay, of n, or excuse me, I'm going to find the limit. That's what I'm going to do. I'm going to take the limit as n goes to infinity, okay, of n to the 4th minus 6 over n to the 9th plus 3n squared plus 4n plus 1, okay, and I'm going to divide that then through by, and we'll do n to the 4th over n to the 9th, okay, and so that's going to then equal the limit as n goes to infinity, and we kind of want to remember that little trick that we did before. That's going to end up being then n to the 4th over n to the 4th minus 6 over n to the 4th divided by n to the 9th over n to the 9th plus 3n squared over n to the 9th plus 4n over n to the 9th plus 1 over n to the 9th. Okay? Which is going to then equal the limit as n goes to infinity of 1 minus 6 over n to the 4th, divided by 1 plus 3 over n to the 7th, plus 4 over n to the 8th, plus 1 over n to the 9th. Now, when we take the limits, this goes to 0, 0, 0, 0. Okay, they all go away, and this we're left with 1. So in this case, right, our series is going to end up our limit goes to 1. And so we just need to know, does the sum, n equals 1 up to infinity of 1 over n to the 5th, converges as it is a p series with p equal to 5, which is greater than 1. So a sub n, the sum n equals 1 up to infinity of n to the 4th minus 6 over n to the 9th plus 3n squared plus 4n plus 1 converges. Now I can in fact utilize number 2 with this one as well. Okay? So I have an alternate way of going about this. If I actually use 1 over n to the 5th, I will get the same answer. So let's use 1 over n to the 5th. So we'll take the limit as n goes to infinity of n to the 4th minus 6, okay, divided by n to the ninth plus 3n squared plus 4n plus 1 divided by 1 over n to the fifth. Okay? And so we'd actually end up with getting, right, an n to the ninth minus 6n to the fifth divided by n to the ninth plus 3n squared plus 4n plus 1. And we know that that is also going to equal 1, and the rest of our proof follows out from there. Okay? We would again just state that 1 over n to the fifth converges. That's a p-series with p equal to 5 greater than 1. Okay? And that would tell us that our series converges by the limit comparison test. Let's not forget to put which test we were using. So that's the limit comparison test. All right? You've got 3 different options that will tell you whether or not your series diverges or converges. All right? The trick here is to select, an appropriate series to compare it against, or an appropriate sequence to compare it against, but also to make sure that you're using the right one of these 3 choices. Okay? So if you find that your limit goes to 0, you need to show that b sub n converges. If it doesn't converge, you haven't proven anything. Okay? You have to choose another b sub n. And then on the other hand, if your limit goes to infinity and b sub n converges, then again, you haven't actually proven anything there either. Okay? So you've got to make sure as you're going through and doing this limit comparison test that you're following the guidelines of the theorem exactly. Okay? So this finishes up what we were talking about in terms of the limit comparison test. So here's the question now. Does this series, the sum n equals 1 up to infinity of 1 over 2 to the n minus 1, converge or diverge? And so what we want to do now is we want to notice that this isn't a polynomial. So it's not going to have like the same kind of simple polynomial answer, but it does have a very similar process, right? And the other piece here is because we've got something to the nth power, we're not going to be utilizing a p-series. Instead, we're actually going to utilize a geometric series. So we're going to let, our b sub n equal 1 over 2 to the n, which kind of seems to be a natural choice, because basically the dominant part of the bottom here is just 2 to the n. And so the limit as n goes to infinity of 1 over 2 to the n minus 1 over 1 over 2 to the n is going to equal, and what I'm going to do is I'm just going to make this 1 over, and I'm going to divide 2 to the n over 2 to the n minus 1 over 2 to the n. Okay, and that'll take that limit as n goes to infinity. And so this ends up equaling 1 over 1 minus 1 over 2 to the n. Okay, and we'll take that limit as n goes to infinity. All right. And this thing here, right, is just going to end up equaling 1 over 1, which equals 1. Check. Right? So it actually equals a value. So now we just need to know, what about 1 over 2 to the n? Does that converge? Well, the sum n equals 1 up to infinity of 1 over 2 to the n is going to end up equaling the sum n equals 1 up to infinity of 1 over 2 to the n, which equals the sum n equals 1 up to infinity of 1/2 times 1/2 to the n minus 1, which is a geometric series with r equal to 1/2, which is strictly less than 1. And so the series, converges. And that finishes it out. So this one, the difference here is that we're going to be utilizing the geometric series instead of the p-series to determine convergence. And we're done. So this completes our work with both the limit comparison test and the comparison test. Okay? Both of them are going to require us to select a b sub n, right? That's appropriate, that will allow us to then utilize the theorems. One of the big things that I can tell you about this is make sure that you are careful with utilizing the theorems exactly as they're written. Okay, so you really want to get comfortable with those theorems, right, in order to prove our convergence to divergence.